Okay, so the idea of this lecture here today is to give you a really brief and informal introduction into the particle filter, which is an alternative methodology compared to the Kalman filter, which were restricted to Gaussian distributions. So all these Gaussian filters, so the Kalman filter and all its variants, always just say we have a Gaussian distribution. So they always assume we have a Gaussian, and they were only able to maintain this Gaussian distribution. So the particle filter wants to go a different way and say, what alternatives do we have? Can we actually represent arbitrary distributions? So how does an arbitrary distribution look like? It can be something written here, let's say something which looks like that. And the question is, how can we actually represent that well by in alternative way? So what are ways for modeling this distribution? And since I want to maintain arbitrary distribution, it should be clear that kind of a parametric form is usually not well suited to do that. So assuming whatever some exponential function, a polynomial, or whatever I'm using. So whatever function I put in there can actually perfectly violate the assumptions I did before. Therefore, one way to address this was just using samples. So just, let's say, points in the space, and let's say the more populated some part of the space is, the higher the probability. And the less populated part of the space is, or volume of the space is, by sample, the less likely it is. So we can actually say, let's take the distribution we have here and represent it by samples. Say this is the probability of that variable x here. We can have samples here, and the bigger the value is, you can see that as the more samples we have, or one sample with a higher weight, the more likely it's that area over here. Of course, this is absolutely an approximation. So I can, if I, for example, cut out a small area between two samples, say, what's the probability of this area here in between? I look up here, oh, it's a pretty high probability here, but there's no sample in this small space. So it's clearly a technique which approximates the distribution, but it gives you the full flexibility to represent an arbitrary distribution. Just the more samples you use, the better your approximation is. Okay, so let's be a little bit more concrete. We can say we have a sample set, and the sample set contains of one, let's say, state hypothesis. This is one sample in the state space, and it may also have a weight or an importance weight, WI. And we simply have n of those samples, and we want to represent probability distribution. And assuming that the more samples we have in an interval of the state space, the more likely that interval is, that the event or the variable, the value of that variable corresponds to that, the value in that interval. And so if we express this as a probability distribution or probability density function, P of x is a weighted sum of all samples, and then it's a Dirac distribution in the point. So it's kind of extremely peaked in that single point, and so the Dirac distribution is peaked only in one point and 0 outside, but the integral of it is 1. So we have kind of a lot of peaks in the state space. So if I integrate over all of them, because it's a weighted sum, it turns out to 1. And this is kind of the way the probability distribution is represented. So two examples over here. So this is, for example, a Gaussian distribution here, and this is some other function. You can represent them by samples, so you see the samples as lines down here. And the more samples you have in an area, the higher the probability. You see if kind of the interval you use for testing is very small, so kind of very small, like this one. I would assume here's 0 probability, although the function is not 0 probability. But the bigger I make my interval and kind of move here towards, the better it actually approximates the function. And here you can see also in a way, here's a peak and here's a peak, so there are more samples densely represented here. So the more samples or particles that fall into one of those intervals here in x, the higher the probability of this area is. It's kind of the key thing the particle filter uses. So one of the questions is how to actually obtain these samples. How to get those samples that they represent this distribution. So if you take your random number generator, you find your computer, then it gives you a uniform distribution. So all positions are the same likelihood. You may still remember in the, I'm not sure if I did did that at the beginning, but at least those of you who have attended Robotics 1, that there are some functions or some probability distributions for which you can effectively draw samples, and one of them is a Gaussian distribution. So from a Gaussian distribution, you can very, very effectively generate samples. But if I come up with whatever fancy distribution I have, or something which looks like this one over here, the question is, how do I actually obtain samples from such a distribution? Well, there's something which is kind of an important principle that these non-parametric sampling approaches use, which is the so-called importance sampling principle. And that actually tells you that you can actually, to obtain samples from a function f, you don't need to generate these samples from that function f. You can take a different function, function g. The only thing you have to do is you have to then kind of account for the difference between the function f and the function g. And this is done by weighing the samples. So you can see it that way. Let's say the blue function is a function we want to approximate, from which you want to generate samples. This is what's called the target distribution. However, the only two functions we have in our computer is sample Gaussian and sample uniform. So we say, okay, we can actually say this is at least closer to a Gaussian than to a uniform distribution. Let's take the Gaussian. Let's take the red function over here and use this as a so-called proposal distribution. And the proposal distribution is a distribution you select, and this is the one from which you're able to draw samples in an efficient way. And then we actually draw samples from this red curve. So these are actually all the samples shown in here. The only thing which the importance sampling principle then says is account for the differences between those distributions by assigning a weight. This is proportional to the difference between those distributions. So the weight is f divided by g at that point. So if I have drawn a sample here, I take f is this value divided by g is this value. It's approximately 2, because kind of the difference here is, so this function is approximately twice as high as this one. And in areas where they're the same, the ratio is approximately 1. However, here's an area where there's a big difference, so I have high values here. And this accounts for the fact that it's quite unlikely to draw a sample here if I draw from the red distribution. However, this sample needs to occur very often according to the blue, so I simply give it a higher weight. So this particle simply has a higher weight, although of course there are less samples here than area. This is what the importance sampling principle tells us. If we want to approximate f, but we can only generate samples from g, I'm happy to draw samples from g and then weigh those samples by f divided by g in order to take into account the differences between them. Yes, please.
How we should calculate the mean and variance for the Gaussian here? For some, how
you have to, so the proposal distribution is a function that you are going to provide. You can also take a uniform distribution. The only problem is, for a uniform distribution, you will generate a lot of samples very, very, very far away, and this will then get a weight of 0.
Here we have blue function, but for Gaussian, we need a mean and covariance to put under this.
Yeah, you have to specify this. Is the choice of the designer to do that. And what you can do is you can take a few, for example, take a few points on the blue curve that approximate it, but that's completely up to you. So the user or the designer of the algorithm specifies the proposal distribution, because that's the function he or she wants to sample from. And then we just the same picture a little bit bigger, so that you can see here the samples and the weighing of the samples a bit better. So this gives the weight here, the position of those samples. And this kind of trick, the importance sampling principle, is key to the particle filter. So the particle filter wants to do state estimation, the fashion of a recursive based filter, using that principle. So not relying on kind of a mean estimate and a covariance, but use only these particles to represent the belief. So they are also a recursive based filter. They are a non-parametric approach. That means they are not restricted to the Gaussian distribution, because given the samples, I can approximate arbitrary distributions. Of course, you may need a very, very huge number of samples. So if your state space is high dimensional and you have some weird form, you may need an infinite number of particles. You can actually show if you push the number of particles to infinity, the approximation error goes to 0. But reality, we don't have the capabilities to maintain an infinite number of particles. So we're always restricted to a finite number set of particles. And if you look to the base filter, how the base filter was done, so we had prediction step and an update step. And if I transfer that here to the particle filter, the prediction step is drawing samples, sampling from the proposal distribution. This can be seen as the prediction step if you take the particle filter and look at the analogy in the base filter. Then drawing samples from the motion step, from the motion model, or from the update step, from the motion step, prediction step in the base filter, corresponds to sampling from the proposal distribution. That's your first estimate what your target distribution may look like. And then the update step is assigning a weight that is proportional to the ratio of the target divided by the proposal distribution. This could, for example, be so I generate samples, possible positions where the robot is according to its motion, and then I kind of weight those particles on how well do these particles or positions actually explain my observations. Okay, so the particle filter algorithm in brief says, the first step, it says, sample particles using a proposal distribution. If I look to the analogy of the base filter, this is the motion model for which I generate my samples. This is my proposal distribution, typically called pi. So I generate new samples according to the motion. Let's say if the robot was driving 1 meter forward, I propagate my samples approximately 1 meter forward. Some a little bit less, some a little bit more, and this counts for the noise I typically have in my motion. Then in the second step, I compute the update weights, the weights, and this is kind of the step which corresponds to the update step in the base filter. And what it does, it takes the target distribution, so the thing I want to approximate, and divides it by the proposal distribution. And it turns out for the standard, let's say, case of localization here, if you take as the proposal distribution the motion model, P of xt given xt minus 1 ut, then this target divided by proposal is a term proportional to the measurement model, so P of v given xt. So you update the weight for every particle, so you have a weighted set of particles, and then comes this magic, what's called resampling step. What the resampling step does is it replaces particles which have a high likelihood, the replaced particles with a low likelihood by particles with a high likelihood in a very informative way. You can see this is survival of the fittest principle. So if you have a particle with a very, very high weight, the resampling step will actually kind of reproduce this weight, so replicate this, and then forget about particle which is a very low weight. This needs to be done because we have only a finite set of particles, and what can happen is that all the particles go to areas of the state space which are very, very, very unlikely. So I kind of want to let those particles die over time and replicate them by particles which actually cover the interesting, the good areas of the state space. This is kind of what the resampling step does. If we would have an infinite number of particles, we wouldn't need that this resampling step. But since this is not the case, we actually need them. So exactly these three steps can be seen as in the standard particle filter algorithm. So this is the old particle set, your motion commands and your observations. You compute kind of a predicted set. You iterate over all samples. You sample from your proposal distribution, and this proposal distribution typically takes into account here the UT. Then you compute your weight, saying it's my target distribution divided by the proposal distribution, evaluated at the position where the sample was drawn. And then I add that to my particle set, the weighted particle. This is the prediction step. And then I do the update step. No, I'm sorry for that. This is the prediction step, and this is the update step already, but both in one. What's down here is the resampling step. The resampling step says I have my set of samples, I have n samples, and I just draw n samples with replacement from that set, and sampling a particle is proportional to its weight. So if a particle has a weight that is twice as, if particle 1 has a weight that is twice as big as the weight of particle number 2, particle 1 is twice likely to be drawn. And then I do that, and then I end up with a new set. In this new set, I set all the weights to 1, or to 1 divided by n. And then I have again my particle set where every particle has the same weight, and I continue with the next step. It's kind of the abstract particle filter algorithm. Let's be a little bit more concrete and look into localization, particle filters for localization. This approach is typically called Monte Carlo localization, and it's kind of one of the absolute standard approaches for localization. So most localization systems actually work with that principle today. So each particle here represents the pose hypothesis. So an x, y, theta location where the robot is currently in the space. So if I'm here, I'm the robot, I'm standing here, I assume there's a lot of particles, let's say, concentrated around the pose where I currently am, and less or basically no particles cluttered somewhere in the space. What the proposal distribution is often chosen to be is the motion model. So P of xt given xt minus 1 and ut. So if the motion model says the robot went 1 meter forward according to the odometry command, I will move all those particles approximately 1 meter forward. Some a little bit less, some a little bit more. This depends on the motion noise I have. So if all particles concentrated here in that space and I just go forward, 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 all particles will move approximately in the same way, but the particle cloud will kind of spread out given the uncertainty that the motion has. This is the first step. Then I do the correction step where I divide the target by the proposal distribution. And here for the particle filter you can actually derive that this is a term which is proportional to the observation likelihood. So P of that t given xt and the map. So for every particle which is distributed in space, you look how well does this position of the particle explain the observation I get. How likely is it to get, given that the robot is here, that it obtained the observation the robot got. So you can say you determine the particles which are well in line with the model and the observation. And those particles where the observation perfectly fits to the map, you say, these are particles which are pretty good, they get a high weight. Those particles which are drawn in completely stupid places, because I've drawn from the motion model, not from the distribution I want to approximate, they will get a really, really low weight. So if the robot measures, it's looking in this direction and says, I'm 10 meters away from a wall, but here the wall, according to my map, is 3 meters away, these particles very likely get a low weight. And then the next step is again the resampling step. So if you look to the particle filter algorithm for localization, it's exactly the same algorithm I've shown before. And the only thing is that here the sample is generated from the motion model. So I take the previous pose of that particle and apply the motion, and then the noise term, and then I end up in the new pose. And then the weight is computed according to the measurement model. And the thing in the end needs to be normalized, therefore goes proportional to it. This is kind of the implementation detail which is hidden in here. There's a reason why before it was proportional to here is equal. You just need to normalize it. And if you do that, you end up with an approach. So this is every of these red points show a possible position of the robot. The robot is in reality here, and it takes approximately this movement. And what you see in this video very soon is that the particles here, which are spread all over the place, accumulate in certain areas, and then it's because they are kind of consistent with the observations and the robot's movements. And some point they kind of die out, and then so you see how the filter evolves. After a few steps, you see all the probability masses here concentrate in that corridor. At some point in time, you actually see that only 2 hypotheses are left because the corridor is symmetric. The 2 ways that the robot can be, so this one and this one. And then the robot is entering one of those rooms, and then you see that this particular cloud will die out because this room simply looks different to this room over here, and only the particle cloud here survives, and the system is kind of progressing here, estimating the pose of the robot. Now this is Monte Carlo localization, one of the really standard approaches to localizing a robot, and one of the kind of applications which make particle filters in robotics very popular. A few words about the resampling step, because kind of the motion model you already know, the measurement model you already know. We did that in the second week, did kind of the short repetition on the motion models and the measurement models. These are exactly the models which are used in here, and also the same that we used for the Kalman filter, like this function G and this function H, exactly the things we're actually using, the probabilities which are the resampling principle is kind of what I said before, it's kind of a survival of the fittest principle, and it kind of replaces unlikely samples with more likely ones. And it uses this kind of trick in order to avoid that all the particles concentrate in low likelihood areas of the state space. And I need to do that because I only have a finite number of samples. However, there are different ways for realizing this resampling step. The first thing is you can actually treat that as a roulette wheel. So you can see this as a roulette wheel, and the size of the buckets where the ball can fall in is proportional to the size of the particle weight. So this corresponds to particle 1, is the width, weight 1, weight 2, weight 3, and so on until weight n. What we then can do is we can, if you of the analogy to the roulette wheel, you take a ball, throw it in, and repeat that n times. And depending on the bucket where the ball ends up, there's a particle you put in the particle set. So if you do that, say the first ball ends up in bucket 1 to 3, and then you simply continue this process and so on until you did that n times. So it's kind of a standard roulette wheel application, and you can actually implement this with binary search, and so you can do this in n log n. So you draw a number between 0 and the sum of all weights, and then you binary search to end up in the interval. So you can implement this in n log n, this resampling step. However, there's a better way to do that, and this is you can see this as a kind of roulette wheel, but now don't consider it kind of the ball, but you consider this as a number of errors, an equal distribution of errors, where you have n errors corresponding to n particles, and you just draw this only once. So you draw this only once, turn the roulette wheel, and then you pick all the points where the arrow points to. So you just then draw one random number, and then deterministically select the buckets. You will still end up having the property that a particle is more likely to be drawn if it has a bigger bucket. And so you have exactly the same properties in terms of you draw a particle proportional to the likelihood, to a likelihood that is proportional to its weight. And you can continue doing this. This is called stochastic universal resampling. The advantage, you can implement this in O of n, so faster than n log n, that's one advantage. But the most important property is if you have a particle set where all the weights are approximately the same, this approach will actually replicate the original set. So let's say all these weights W1 to Wn exactly of the same size. You select kind of the first one somewhere and then go 1 divided by n steps further, you will reach every sample. So every sample is perfectly replicated, which makes absolutely sense, because if all particles have the same weight, there's no mean for you to say this one is better than the other one, and I should replace this one by the other one. In this approach, however, it can happen that you draw a sample multiple times and neglect another one. So you have a kind of a low variance resampling. And this makes it a much better technique, not only because it's faster to compute, but also leads to better particle sets. And this is especially the case when you have situations where, for example, for a certain period of time, your observations are not well suited to tell you which is the good particle, which is the bad particle. Let's say you have the environment is simply, the sensor is currently not able to tell you which position is best among the particles, or which is the good particle, which is the bad particle. They all get roughly the same weight. In this case, this resampling technique is key to success. Otherwise, it's very likely that you just by chance eliminate the good hypotheses where the robot actually is and don't replicate. The other thing is you can actually implement that quite effectively with just one for loop. I don't want to go to the details. So what the key thing is you draw just one random number, that's kind of where you start, and then you just jump by 1 divided by n from this random number through your kind of roulette wheel in fixed distances. And what you're doing here is you kind of actually compute, you always add up the cumulative distribution of the weight. So W1 in the first bucket, W1 plus W2 in the second bucket, and so on. This is kind of computed here as a step. And then you always select the particle whenever the drawn number plus the number of times you added 1 divided by m corresponds to this cumulative function. So small illustration again how this may look like. So you may initialize your particles like that. You obtain an observation. Yeah, this one over here. So this is where the robot is here in reality. This is not over here. Oh no, this is actually the most likely particle here. So then you do the resampling step. Then you continue the motion update. You can see some particles faster already together. Then you measure again. Do the weight update. So you don't see any change in here. There's weight update. The particles have all the same size, not as strong. You do the resampling step, quite some samples die out. You continue this process. Motion update, take a measurement, do the weight update, and do the resampling step. And then you continue with this process all over the place until you get more certain, more certain, more certain. And you continue this process, and this is kind of the standard technique for estimating the pose of a particle, of the robot in a known lab. So this is localization, not at all SLAM, but we'll actually exploit the Keyes idea of the particle filter to apply it for the SLAM problem, but that's something we're not going to do today. So kind of to summarize particle filters, what the particle filters do, they're form of base filtering, and the most important thing is that they're not restricted to a special distribution like a Gaussian, the so-called Gaussian filters did, but it can represent arbitrary distributions by using this non-parametric representation of having these samples. And so we use a proposal distribution which we as a designer of a particle filter can actually set. And this is used to draw samples, and then I have to compute the target divided by the proposal distribution, which allows me to compute the update. And this works especially very, very well for low-dimensional spaces, such as localization. The third space is only 3-dimensional. There, these sampling techniques work very well. If you go to very high-dimensional spaces, you have the problem that you would need a huge number of samples to cover this high-dimensional state space very well. That's kind of the problem of those particle filters. So they work very well in low-dimensional spaces and can represent arbitrary distributions. And if you look to the special case of localization, because we actually will build on top of the idea of doing particle filter localization next week to bring that towards SLAM, is that the particles are propagated according to the motion model, and the importance weight is computed to proportional to the observation likelihood, and this technique is so-called Monte Carlo localization, one of the standard techniques, kind of the gold standard for localization today. So next week we are going to use exactly this idea on how to localize with the particle filter to actually set things on top of that and do SLAM with the particle filter. So whenever you've never heard about the particle filter, you haven't covered that in the previous course, heard about that, it may make sense to just, until next week, study the particle filter a little bit. There's also an exercise sheet which covers that. And I recommend, again, the Progressive Robotics book, chapter number 3. There's one subsection of the particle filter. So if you feel not confident with what you've heard here, it's very confusing to you, I advise you to go to the library and reread that chapter again, because this is kind of the basis. We will actually exploit the particle filter in the next weeks for the SLAM problem. We won't dive in all the details of the particle filtering, but you need to at least have an understanding what's going on to have a chance at least to understand the particle filter-based SLAM approaches. But the nice thing with these particle filter-based SLAM approaches is that you don't need very complex matrix multiplications, matrix inversion lemma, and all these things. So you have all points estimate, you can very easily manipulate those points estimate. And this kind of helps it to understand it quite quickly. So I think it's actually much easier to grasp than the Kalman filter and all its variables. Okay, thank you very much.